All right, so in class we've been working with things. So what I would like to do is I'm going to set up some things on YouTube, and 1, 2, 3. And the purpose of this video is to briefly review everything we've done, and then to do some more examples because I know some of you need it. So what I'm going to encourage you to do is to download the notes that will be attached, and I would encourage you to write on this. I would encourage you to do the problems, pause the video, do the problem, even if it's step by step, check your work, and then use this to help your learning. And then all of this should go in your class notebook, your spiral notebook. All right, so we want to be able to look at the shape of a graph. Well, when we're talking about the shape of a graph, that's using normal language, but mathematically what we care about is, hey, where's the graph increasing? Where's the function increasing? Where's the function decreasing? Does the function have relative extrema, mins, maxes, global extrema, mins, maxes? Where is the function concave up? Where is the function concave down? Does the function have asymptotes? This is where we're going. So right now we're going to be using the derivative. We're going to start with the first derivative. So if you really think about this, right now, all we're going to look at is, if I really want to think about it, is I have a house. Okay, I did this in class. And the function lives on the basement floor, right, the first floor. Well, the first floor above it, the second floor, models the first floor. So f prime of x will tell you stuff about f of x. Now, today we're going to work on intervals of increase and decrease and how the derivative helps us. Now, previously we've done lots of investigations, and we learned that if the derivative was positive at a point, the function was increasing at the point. And we learned that if the derivative was negative at a point, the function was decreasing at a point. So some people call this the increasing-decreasing test. And it basically says this. If a derivative is positive on an interval, the function's increasing on the interval. If the derivative is negative on an interval, the function's decreasing on the interval. Now notice the sign of the derivative is important, and it informs you how its predecessor, its function, is decreasing. So some things become important. First of all, if you think about this, what number lives between positives and negatives? 0 does. And it didn't really dawn on me until I started thinking about talking about Rolle's theorem. And if you look at Rolle's theorem said, hey, if you have a function that's continuous on a closed interval, differentiable on the corresponding open interval, and the y values are the same, you will have a horizontal tangent line somewhere on that interval. Well, if you really think about Rolle's theorem and what it's saying you're going to have a relative min or a relative max somewhere on that interval, and it could be global. Well, and then if you take a look at Rolle's theorem, you're going to notice it's very restrictive. So what people do is, when they're generalizing theorems, they make it as rigid as possible to get a result they want, and then they start peeling off things to see how much they can get away with. Well, in Rolle's theorem, differentiability on an open interval is required. Someone peeled that off, and then they learned that you could also have local extrema at points in the domain where the derivative doesn't exist. Well, typically that's going to be a corner or a cusp. And then from there, Fermat proved that if you have a maximum or minimum, locally of course, the derivative is 0 there. The converse isn't necessarily true. Just because the derivative is 0 doesn't mean you're a local extrema. The simplest example is the parent function for the cubes, y equals x cubed. At 0, the derivative is 0. Okay? But it's not a local extrema. Okay? So then someone developed the idea of critical points. Now remember, a critical point is a point in the domain of a function where the derivative is 0 or the derivative does not exist. Well, critical points are candidates for relative extrema. A lot of people sometimes think they are local extrema, and they're not. They're candidates for local extrema. Quite often they will be, but they're not. But what I think is a little bit essential to know is critical points serve a very useful purpose. They break the domain into little intervals. And the math word for breaking the domain up is called partitioning the domain. And then you can test a point in each of those open intervals. And if the derivative is positive at that point, the function's increasing on that whole interval. If it's negative at the point, the function's decreasing on the whole interval. So this is a very important process. Okay, now to the examples. Now, one of the things I'm noticing is a lot of people aren't thinking about the domain of a function. That's very important. So here, g is a polynomial. So we know that g of x's domain is all reals. So the first order of business is we want to just look at working on finding intervals of increase and decrease. Okay, so here we go. So we want to find the critical points of g. So I start by finding the derivative of g. And let's see. We'll have 15x squared plus 10x. And we're going to subtract off 30. Looks like the greatest common factor is going to be 5. So let's factor. Yeah, 5. So that's going to be 5 times 3 is 15. Don't forget the x squared like Mr. Isaac. 5 times 2. Okay, and 6. Okay. Now, what's the mission? All right, so we can try to split the linear term, and when you want to do that, you take the coefficient of the square, 3, times the constant. So that's negative 18 and 2. Do we have any factors of 18 that are 16 off? We have 1 times 18, that's 17 off. We have 3 times 6, nah, that's too close. And we have 2 times 9. So this isn't factorable. So I'm going to use the discriminant from the quadratic formula. That will immediately tell me how many roots I have. So b squared, in this case, I better put a colon here. So that would be 4 minus 4 times 3 times negative 6. Now, a negative times 2 positive and a negative is positive, so this will be bigger than 0. We have 2 real solutions. Okay. Now, we're going to practice finding the solution, but I'm going to let you graph it. So you can use your calculator too, because some of you need that practice. So this is 4 plus, let's see, 18 times 4, so it's 72. Okay, let's double check that, 18. And then you 40 and 30, 70, good, and that's 76. And that's not a perfect square. Okay, so x is equal to the opposite of the linear terms, okay, opposite of the linear coefficient, excuse me, plus or minus the square root of the discriminant, 76, over 2 times the coefficient of the square term. So we have 2 roots. In fact, I'm now going to just graph these. We'll find, and I'm going to have you get those in a second. We'll put that over here. We're going to go g prime of x equals 0. Okay, so if you think about this, and I'm already going to graph g prime, okay? Because I want you to think about this. We have 2 zeros. So maybe one of them's here. We'll call that x1. And we'll call this x2. So x1's the smaller. We know those are zeros, okay? So I know the quadratic intersects the x-axis there. Now, this coefficient is positive, so it opens upwards, which means the vertex is underneath the x-axis and between these roots. In fact, it's the midpoint of this line segment connecting the line segment for these 2 roots. That's going to be the x-coordinate, and also the axis of symmetry is going to run through there. I'm multiplying by a positive, so that's still going to be the product of 2 positives. Well, that'll be positive, so that takes care of the ends. And the product of a positive and a negative is negative. So I could technically, I now know where I'm going with this. So I'm going to write g prime of x equals 0. And then I'm going to write x1 equals, and I'm going to write x2 equals. I've done the work up here so you know how to find it. So you get your calculator out, you're going to notice, if you look at what I've done, I just graphed the quadratic after I factored the 5 out. Now, I found the zeros. So what you do there is you go to Menu, you go to Analyze Graph 0, and since there's only one function, okay, see, I just did it again. So I did it twice. And now let's take this attributes, let's get another, okay, so now I'm going to write negative 1.786 and 1.119. I truncate, you could round. Remember, you must have 3 digits, okay? Now, where some of you are having issues is looking at signs. So if you have to, write g of x here. The derivative is positive, so it's increasing. The derivative is negative, so it's decreasing. The derivative is positive, it's increasing. Okay? Now, g is increasing on the open interval from minus infinity to x1 or x2 to positive infinity. Now I'm going to stop there for a second. The reason I can get away with that is I told the reader what x sub 1 is and x sub 2 is. Because g prime of x is positive on, and now I repeat the intervals to be paranoid so they can never take anything away from me. Okay. Now let's do g is decreasing on, and notice, you look right here, where's it negative? It's right there, but here's your check. X sub 1 to x sub 2, because g prime of x is negative on, and I'm going to plagiarize and re-copy that interval. Okay. Now what I would like you to do is pause this video. I want you to go and I want you to graph g of x right here. Okay. I would also like you to graph g prime underneath it. And I want you to observe that when you look at the graph of the derivative and the function together, you're going to notice that the zeros of your derivative, if you were to draw vertical lines through them, will match up with the domain values of your relative extrema. Now notice, let's go to algebra 2 now. G of x changes behaviors at this value, which means, since g of x is changing behaviors, that is a relative, a local extrema. So since we're growing, we're increasing, and then we decrease, that's a local max, a relative max. Now you're decreasing and you're increasing. That's a valley. That's a local min, a relative min. So every time we do one of these problems, I want you to graph it if you can, and I want you to start asking yourself questions. How do the zeros of the derivative relate to the critical points on the graph of the function? So you can start to make connections. Okay, now, look, we have another problem here. Oh, look, it's another polynomial, so you should know that the derivative, now this one we're going to use technology on because when I made it up, I probably should have done it a different way. So I want to make our lives reasonable. Okay, so G's domain is all reals because it's a polynomial, and you need to know that you need to work on your domains. So I'm going to go find the critical points. The critical points of G are where G prime of x is 0 or does not exist in the domain of G, in this case, all real numbers. So 16x cubed minus 14x squared plus 16x plus 8. I know 2 goes into everything, so let's just get that out. So that'll be 8x cubed minus 7x squared plus 8x plus 4. Now let's put some parentheses there and put a 2 there. Oh, okay, now this one we're going to use technology on because this is going to be ridiculous. And let's go ahead and do this a little bit differently. Now on the Inspire, if you hit doc and you go, I'm going to insert a new problem, Mr. Isaac, it'll clear everything out. Let's do a graph. And now, did you know on the Inspire you can actually name your functions? So you can come over here and you can name this g of x. I wish you could do the other one as g prime, but you can't. So we can do this one. So 16x cubed. Okay. Then we, oh wait, might help if I actually don't almost type the derivative there. That would have been really tragic. 4x to the fourth. Okay. Now, okay. Then we're going to subtract 14x cubed. Okay. Then we're going to add 8x squared. Whoa, I have no idea what I just did for that to happen. And we have to. And then we're going to add 8x. So for the function, you can see x equals 0 as a root. Okay, and press the down arrow. Now that'll graph it. What happened here? Why is this? Okay, now we got out of there. Good. Now I'm just going to type in the derivative here. Well, actually, let's just do it this way. You type in the derivative, but I'm going to practice using my calculator because I did find the derivative. I want you to practice that skill because that is important. Okay. Okay. Whoa, that's a hot mess. Okay. So now what we're going to do is we're going to take this hot mess and make this more reasonable for us. So the first thing I'm going to do is clean up this window. All right, window settings. I think I can go from -7 to, let's try 6. We'll count by ones. Let's do -6. Let's go to 25. And we'll skip count by 5s and let's see. Okay, is that reasonable? There we go. Now, notice the function g is this light blue graph. Look, I have a local min here. And look, it matches up with the 0 of the derivative. Hey, look. Okay, let's see. We have a local max there. And it's going to match up. Oh, wait, wrong graph. We have a local max there, and it matches up with the domain's value, the 0 of this derivative. Local min, oh, look. And the 0 match up in this case. How interesting. I just made this problem up. And actually, I could even zoom in more. Okay, now, one of the skills you can use on your calculator, regardless of whether you have an 84 or an Inspire, I'm going to hit the tab button. If I go up momentarily, and I just click on that arrow to turn it off the button, notice I just have the derivative. That'll make it easier to use my commands. Menu, because I know I'm going to find the zeros. Analyze graph, 0. Boom. Boom. There's one. Menu. Analyze graph. 0. Boom. Boom. Menu. Analyze graph. 0. Boom. Boom. Okay, we did have one nice root. Okay. Now, let me write that on some paper so I have that. 0.277. 0.902 and 2. Okay. Now, oops, I'm going to have to take that out. Darn it. Okay. Now, so I'm going to go g prime of x does not exist. There are no values. G prime of x equals 0, so I'll write that out. Then I'm going to write x equals -0.277, x equals 0.902, and x equals 2. Okay. Now I'm going to make a sign chart for g prime of x, colon. Now I'm going to draw my number line. Now, you know what? I'm going to come down here and I'm going to subscript these so I don't have to write those numbers because I'm running out of room. And above the number line, this sign chart, I'm going to put zeros because that's the type of critical values they are. They're zeros. Now, I'm going to use the graph here to help me. So I'm going to go from -infinity to 0. So I go to the graph. It's negative. Then it goes to positive. Then it goes to negative. Then it goes to positive. Okay? And notice on my paper, okay, So if you need to, you're going to come over here, and that means g. So if the derivative is negative, it's decreasing. Positive, that means, okay, the derivative is positive, that means the function's increasing. Negative, if g prime is negative, excuse me, the function g is decreasing. Oh look, g prime is positive, so the function's increasing. Now I want you to pause this video, and I want you to go write your sentences like you've done before. So now notice I've answered the question, but it's not justified. So I would not get full credit. So now we're going to do the y. Why? Oh, the function's increasing, so the derivative, g prime, is positive on, and then I repeat, I copy the intervals. Okay, let's make sure I read this correctly, because since I turned it backwards, I might have flipped these, and I don't want to do that to my young adults. Okay, so I'm going to pause this and double check that I copied it right. Yes, I copied it right. Now, here, I'm going to write my justification. G prime, okay, the function's decreasing, so the derivative is negative. Now notice the previous example I used inequalities. This example I wrote out the words. I would encourage you to do it both ways just so you get the practice, so that on the day of the exam you have multiple opportunities to do this. Okay, now this one I want to do a little bit differently. I want to graph it, because if you look at our first two examples, our critical values that we had only were zeros of the derivative. And then, when we give all these students these problems, they start to think, oh, then critical points are only zeros. Well, whoa. You're going to see something interesting here. So notice I get my Inspire out. I'm going to go to Document. I'm going to go to Insert. I want to insert a problem. I want to insert a graph. And I'm just going to call it f of x. So, we have a parabola. Right? We have a parabola on the interior function, and then we're raising it to a power. So we have a composition of functions. Now, I'll go through the logic of what the domain is in a second. So x squared, then I'm going to take away 3. And don't forget to close the parentheses, and my power, I believe, is 2/3. Now look at this graph. Do you see a cusp in two places? So when I look at this graph, since I see a cusp here and a cusp here, I know the function is not differentiable there. So as you come from the left to where this domain element, notice you're decreasing, so your derivative would be negative. Now as you get closer, it's getting steeper here. Notice it's getting very steep at the beginning and starts to slow down, but it's positive. So the graph should have a vertical asymptote there. And this is going to have a vertical asymptote there. I should have a horizontal asymptote here. So my critical points, I'm going to have a 0, and I'm going to have two places where the derivative does not exist. Okay, now let's reason through the domain. Okay, this is a composition of functions. So the theorem I'm going to want to use is the composition of continuous functions is continuous. Okay, the outer function is a power function. But what catches my attention is it's a cubed root. And that's important. Since the denominator is 3, it's a cubed root. And you can take the cubed root of a positive, a negative, and 0. So since this domain is all real numbers, doesn't matter. This is going to exist. So the domain is all real numbers. So please write that down on your paper. Now let's go. Okay. And I'm probably going to have to get some paper here in a second. Okay, so g prime of x is, okay, so it's going to be 2/3. Now I'm going to x squared minus 3 to the minus 1/3. Now this is where students get into trouble. And then times 2x. So I'm going to clean this up. 2 and 2 is 4. Don't forget your x. But since this is a negative exponent, okay, and now it's 1/3. Okay. Now, the first thing we're going to do is g prime does not exist. If, okay, I have an algebraic fraction, so the denominator catches my attention. If you really think about it, this will never be 0 because that's a 3. here, what's driving this is the radicand. So it'll be 0 if the radicand is 0, and then you should note that x, when I take the square root, is the absolute value of root 3. So that says x is plus or minus root 3. Okay, now g prime of x is 0. That says, okay, I have an algebraic fraction. The only legitimate place to have a 0 is the numerator. So 4x is 0, so x is 0. Now look, if I'm going to model this, and I'm going to write more than I need to, some people can't do all of this at once, so look, I'm going to say, think about 4/3 x. As a function, that would be a line. Its 0 is legitimate because it's in the numerator, so it's at 0. Any number I substitute into that expression that's bigger than that is this product will be positive, and any number to the left when I multiply it by 4/3 is negative. Now all I have to worry about is the cubed root of x squared minus 3. Now this isn't bad, so hold on. So you know you have two zeros, so let's do this. Root 3 negative, root 3 positive. Now I'm not going to put zeros there. These are zeros for this function y equals the cubed root. Okay, for some reason it stopped, so I had to stop. Now look, if I take 0 in here, if I square 0, it's 0. 0 minus 3 is negative. The cube root of a negative 3 is negative. So if I take, now I can do both of these together because watch what happens. If I take 4 or negative 4, when I square it, I still get 16. And 16 minus 3 is positive. And the cube root of a positive is positive. Okay, and now underneath this, I'm going to go g prime of x. And I'm going to draw a sign chart. I'm going to go ahead 0 minus root 3. This is where now I put d and e there because it doesn't exist. D and e here because it doesn't exist, root 3. And I put these in all the number lines. The quotient of a positive and negative is negative, therefore g is decreasing. The quotient of two negatives is positive, so between negative root 3 and 0, it's positive, it's increasing. Oh, look, on this interval we have a product of a positive and negative, which is negative, so we know g is decreasing. And look, over here the product of two positives is positive. Oops, let me just write positive there. Now look, I've had students that they say, hey, Mr. Isaac, could I just draw pictures? Hey, let's go ahead and do that. It's decreasing, it's increasing. Hey, look, a valley, local min. Hey, now it's increasing, decreasing, local max. Do you see that? Local min. So we have two local mins and a local max. So let's write our sentences. Pause this and write the sentences and then check. So g is increasing on the interval from minus root 3 to 0 or root 3 to infinity because g prime of x is positive on the interval from minus root 3 to 0 or root 3 to infinity. Okay? Boom, full credit. You know, and you know, when's a card when you need one? Because now I'm going to have to go to the back. So I'm going to be decreasing, if you think about it, I'm going to be decreasing from minus infinity to minus root 3 or 0 to minus root 3. Okay, now I'm going to pause it, go write your other sentence, and check it. So I write the stem. Here's the first part. That's correct, but I need to justify. Why? Because my derivative of g is negative. And then you need to go on and you're going to plagiarize your intervals. I almost put the negative in the wrong place. Okay. So now look, a table. Someone's done some work. Let's see what we have here. F is a continuous function on a closed interval from 3 to 12. The function f has horizontal tangents. That means the derivative is 0. At x equals 4 and x equals 9. And a corner. If I have a corner, that means it's not differentiable at 7. So f prime does not exist at x equals 7. So I'm going to make a sign chart. And let's see, we're going to go, now here we don't care about everything, so we're going to go from 3 to 12. So 4, that's a 0, 9 is a 0, and then 7 is a does not exist. So from 3 to 4, oh, they've told us it's negative. From 4 to 7, we're told it's positive. Oh, look, then it's negative, and then it's negative. Uh-oh, look, uh-oh, okay. Now, I did this one intentionally because I wanted to cook the books here. Now, so f is decreasing on the first open interval is 3 to 4. Or, now look, it is true that f is decreasing on the whole open interval from 7 to 12, but I'm not going to do it that way, and I'm going to explain this right now. Because I'm going to use as my justification that the derivative is negative, the derivative of f is negative, excuse me. However, I can't, because at 9, the derivative f prime of 9 is 0. And 0 isn't negative, and 0 isn't positive, it's 0. So here's an example of a critical point, a critical value, a critical number that is not a local extrema. So on my graph, it's a stationary value. All right, because my derivative is negative on, and now I'm going, but I do want to make this point. On this whole open interval from 7 to 12, the function is decreasing. But at 9, the way you'd have to do it is you'd have to use the definition of decreasing. So you'd have to write like a little essay. So you'd use the fact that, hey, since the function's decreasing here, all these y values are bigger than f of 9. Therefore, right, and then on this interval, since it's decreasing, this y value is bigger than all these y values, and then that satisfies the definition of decreasing. But a lot of people don't want to go to that gruff to do it. And now we know that f is increasing on the open interval from 4 to 7, because my derivative is positive on the open interval from 4 to 7. See how that goes? Okay, the last example, I wanted to give you something graphically. So look, the function g is continuous for all reals. Consider the graph of the derivative function below. Uh-oh. Okay, so look, g prime is 0 at 2 values. But what's hidden here is there's a vertical asymptote right here. So g prime does not exist at x equals 1. G prime of x is 0. And now you're just going to, now you write this down. You just can't write those numbers down. Otherwise, the reader's going to say, where did that number come from? Did it just like fall out of the sky? And no, it didn't. Now you see how quickly I came that. Oh, create a sign chart. I'm going to label these x1 and x2. So I'm going to go, hey, g prime of x. Okay. Now notice it's continuous for all real values. So here we go. And where was I? Okay. So x1, that's a 0. And then at 1, it does not exist. And then at x2, it's a 0. Now, you're just going to read the graph. Oh, from minus infinity to this 0, the derivative graph is underneath. So it's negative, therefore g is decreasing. Oh, look, from here, from x sub 1 to the asymptote, look, the y values are positive of the derivative, so it's positive. Therefore, g is increasing. From the vertical asymptote to this 0, all the y values of the derivative are negative, so the function's decreasing. And on the other side of that 0, of the derivative, they're positive. Okay? G